Welcome back to the Deep Dive. Our job here is taking the critical research, the data, the insights you need, and really distilling it down, making it actionable.
That's right. And today we're tackling something huge, securing the entire digital ecosystem. It's a massive undertaking.
It really is. And the scale.
Yeah.
You mentioned, what, 83% of internet traffic is APIs now?
Yeah, something like that. APIs are basically the nervous system. They connect everything, mobile apps, microservices, SaaS. It all hinges on APIs. They're the new perimeter, really.
So if you're building mobile apps, which are essentially just windows into those back-end services,
Then securing that API connection, that's everything. It's the highest stakes game there is right now.
absolutely. So today we're going deep. We're looking at the essential mobile app and API security practices, focusing on, well, what you need to know heading into 2025.
Yep. We want to uncover those layered defense strategies, the things that separate the really robust systems from the ones that are, frankly, vulnerable.
And we're not just talking definitions. We want to get into the implementation, policy engines, crypto on the client side, the practical stuff.
Exactly. Think digital castles, not just walls. We're talking layers. Security that spans the cloud, the network, the code, even the device itself.
So if you're managing products, architecting systems, or just need to get up to speed fast on digital defense,
Yeah.
this is for you. We want to give you that knowledge quickly but thoroughly.
Without the information overload, hopefully.
Right. Before we dive into the threats, though, a quick thank you to our sponsor.
Ah, yes.
Building these modern API-heavy apps is tough. VibeHack provides tools and insights to help make sure your code and cloud are secure from the get-go, integrating security right into the pipeline.
Which is exactly what you need these days.
Definitely. Check them out at vibehack.dev.
No, it's not true.
Okay, let's ground this. You call the API the nervous system. The mobile app is like the sensor what the user sees.
Right, the tip of the iceberg.
But the back end, that's the brain, the data, the logic, all the sensitive stuff. Compromise the API.
And the brain's exposed. Simple as that.
So step one in protecting that system,
Yeah.
getting authentication and authorization straight. Seems basic, but you said it still trips people up.
Oh, constantly. Especially with legacy systems, but even new developers sometimes mix them up. They sound similar, but they're fundamentally different jobs.
Okay, let's nail it down for everyone listening. Authentication is.
Authentication is purely about who you are. Verifying identity. Did you type the right password? Did your face scan match? Is that JWT token valid? It's proving you are who you claim to be.
Got it. Identity verified. Then authorization comes in.
Exactly. Authorization is about what you're allowed to do after you've proven who you are. Can you read this specific file? Can you hit the delete customer button? Can you access the admin panel?
It's about permissions for resources.
Oh, precisely. And every single API call needs a rigorous authorization check for the specific resource being accessed, not just once at login. Every time.
And when that authorization check fails or isn't done right, that's where we hit the big one from OWASP, right? Broken Access Control, or BAC.
Yep. Year after year, it's right up there. It's a massive problem.
Why? Especially with modern microservices, you'd think we'd have solved this.
Well, it's because of microservices, partly. Things are so distributed, you might have dozens, hundreds of little services, each needing its own authorization rules, maybe talking to different databases. Keeping those rules consistent and correct across all of them, it's incredibly complex and really easy for a human to make a mistake. Forget one check in one tiny service.
And you've potentially opened a door to the whole system.
Exactly. And attackers are very good at finding those overlooked doors.
You broke BAC down into three main types. Let's start with the first one. Horizontal escalation. Sounds like moving sideways.
That's a good way to put it. Horizontal is accessing someone else's data, but staying at the same permission level. Think two bank customers, Alice and Bob. Both are just standard users.
Okay.
Alice is poking around. Maybe she sees an API endpoint like AP accounts 12345. That 12345 is her account ID. She tries changing it to 67890, which happens to be Bob's ID.
And if the API isn't checking if Alice is allowed to see account 67890.
Boom, she gets Bob's data. That's classic IDOR insecure direct object reference. It's often simple URL manipulation, but devastating if the backend doesn't tie the resource ID directly to the authenticated user's permissions.
Right. That seems frighteningly common. Now, contrast that with vertical escalation. That sounds more serious.
Oh, it is. That's the jackpot for an attacker. Vertical is moving up the privilege ladder, going from a regular user to, say, a content moderator, or worse, a full system admin.
How does that usually happen? Is it harder?
Generally, yes. It often requires showing vulnerabilities or finding more subtle flaws, maybe exploiting a misconfiguration that leaks policy details, or finding an insecure admin function that wasn't properly protected. Once they get admin rights, though,
Game over. They can move anywhere, steal data, plant malware.
pretty much full control.
Okay, and the third type, context-based escalation. This one sounds tricky. It's about business logic.
Yeah, this is where it gets interesting. It's not just about roles or simple permissions. It's exploiting flaws in the process or the state of the application. The how and when of a request matter.
Can you give an example?
Sure. Imagine an e-commerce checkout. You add 3 items to your cart. The API correctly authorizes the initial cart total. But then maybe there's another less obvious API call, perhaps, for applying a discount code that lets you sneakily change the quantity of an item after that initial price check.
Ah, so you authorize for 3 items, but manage to manipulate the state later to get 4 while still paying the price for 3.
Exactly. The context changed mid-flow, but the authorization logic didn't revalidate or wasn't designed to catch that specific sequence as invalid. Attackers use this to bypass payment steps, mess with workflows. It's about gaming the application's expected sequence of operations.
Wow, okay. That means securing the state machine itself, not just individual API calls. Very complex.
It is.
All right, moving slightly, but related. Broken Function Level Authorization, BFLA. How's this different from general BAC?
BFLA is a specific type of BAC where the application simply fails to check permissions for accessing certain functions or administrative endpoints at all.
So the function exists, like maybe AP-admin delete user.
Right. And maybe the front-end UI hides the button for regular users. But the API endpoint itself, it might have no authorization check or a very weak one.
So an attacker just guesses the URL, maybe finds it in JavaScript files or network traffic.
Yep. They craft the request directly, hit the endpoint, and if there's no proper server-side check for that specific function call tied to their role, they might just succeed. They bypass the UI entirely.
Okay, so the defense here has to be really strict server-side checks on every single function.
Absolutely.
Mm-hmm.
2 key principles are vital here. First, deny by default. No access is granted unless a policy explicitly allows it for that user and that function. No implicit permissions.
Makes sense.
Second, isolate and protect admin APIs. Treat them differently, maybe put them on a different network segment, require separate authentication, and apply the strictest possible authorization checks. Every single request to any function needs that server-side validation.
Got it. Okay, third major threat, and it feels like we'll be talking about this forever, injection flaws, especially SQL injection. Why is this still such a problem in, 2025? GDPR fines are massive.
Up to €20 or 4% of global turnover, yeah. It persists because fundamentally it's about failing to handle user input correctly, treating untrusted data as potential code instead of just data.
Developers under pressure may be skipping sanitization.
Sometimes, yeah. Or using outdated libraries, or constructing SQL queries by just smashing strings together with user input.
Right.
If malicious SQL gets injected into an input field, the database interpreter just runs it.
Leading to data theft, database deletion.
Full compromise, often. And the cleanup, audits, reputational damage, the fines are just the beginning. It can cripple a business.
And you mentioned a scary evolution here, AI-powered injection attacks.
Yeah, that's the cutting edge now. Attackers aren't just trying simple OR 101 tricks anymore. They're using AI and machine learning to probe an application, learn its defenses, and then auto-generate really sophisticated, customized payloads.
So the AI figures out how to bypass the specific filters or WAF rules.
Exactly. It can rapidly iterate through thousands of complex variations, trying different encodings, syntax variations, until it finds something that slips through. This makes manual detection much harder and shrinks the window to patch vulnerabilities. It forces a move towards inherently safer architectural patterns, not just reactive fixes.
Okay, so that need for safer architecture brings us to the next point. We know putting complex authorization logic directly in the application code is messy, error-prone, hard to audit.
Especially with microservices, yeah. It becomes unmanageable.
So the modern approach is to abstract it, pull it out.
Right, which leads us to the concept of a centralized policy engine. And this usually involves 2 key pieces: the policy enforcement point, or PP, and the policy decision point, or PDP.
PPP and PDP. Okay, how do they work together to decouple the logic?
So the PP, the policy enforcement point, usually sits close to the application. It could be middleware in your API gateway, or maybe a sidecar proxy alongside your microservice. Its only job is to intercept incoming requests that need authorization.
Okay, it catches the request, then what?
Instead of the app figuring out access, the PP bundles up the relevant details of the request, who is making it, the principal, what resource are they trying to access, the resource, and what are they trying to do, the action, read, write, delete, etc.
It packages that info up.
Yep, usually as a JSON payload. And it sends that package over to the PDP, the policy decision point. The PDP is the brain of the operation. It holds all the authorization rules, all the policies.
And the PDP just looks at the request details and the rules.
And makes a simple, clear decision. Allow or DDNY, it sends that decision back to the P.
Which then enforces it, letting the request through or blocking it.
Exactly. The application code itself becomes much simpler. It just relies on the PPP's enforcement and the policies. They're centralized, easier to audit, easier to update consistently across all your services. It's a huge win for manageability and security.
Okay, that makes sense. But to make that PDP work, you need to define the rules. You need an authorization model. We talked about RBAC, ABAC, and a hybrid approach. Let's start with RBAC.
Role-based access control, RBAC, is the classic. It's pretty straightforward. You define roles like admin, editor, viewer, and you attach permissions to those roles. If you have the editor role, you can perform editor actions.
Simple to understand, simple to manage, probably.
Generally, yes, but it can be quite blunt. What if you need more nuance? Like an editor can only edit documents they created, or only during business hours. RBAC struggles with that kind of fine-grained, context-dependent rule. It's often too coarse.
Right, which leads us to attribute-based access control, ABAC. This sounds more flexible.
It is, much more so. ABAC makes decisions based on attributes characteristics of the user, the resource, the action, and even the environment, like time of day, location, device security status.
So you could write a rule
Like, allow Principal Alice to perform action. Write on resource.x if Alice's department attribute is marketing, and the resource's sensitivity attribute is public, and the current time attribute is between 9 a or 5 p.m.
Wow. Okay, that's incredibly granular. Maximum control, it sounds like.
It offers potentially very precise control, yes, but
There's always a but. What's the trade-off?
complexity.
Bingo. Managing a complex ABAC system can be a nightmare. You end up with potentially hundreds of attributes and intricate rules interacting in ways that are hard to predict or debug. Auditing becomes really challenging. A small change to one attribute definition could have unintended ripple effects across the whole system.
So it's powerful, but potentially brittle. It can be, which is why many organizations land on a hybrid approach. They use RBAC for the broad strokes defining the basic job functions and then layer ABAC rules on top for the specific context-aware exceptions or data filtering where that extra granularity is really needed.
Best of both worlds, potentially.
That's the goal.
Okay, so you've chosen your model. You need tools to actually build and manage these policies in your PDP. You mentioned two main players, Open Policy Agent, OPA, and Amazon Verified Permissions, AVP. Let's start with OPA.
Open Policy Agent, or OPA, is probably the big one in the open source world. It's designed to be a general-purpose policy engine. You can use it for Kubernetes admission control, API authorization, infrastructure policies, pretty much anything.
How does it work? What language does it use?
It uses a declarative language called REGO. Declarative means you write policies that state what outcome is desired under certain conditions rather than spelling out the step-by-step logic. So a REGO policy might say, allow is true if the input users group is admin.
And applications interact with OPA, huh?
They typically query OPA over a simple REST API. They send the JSON context, principal, action, resource attributes. OPA evaluates that against the loaded REGO policies and sends back a JSON decision, usually just true or false, or maybe some data.
Okay, open source general purpose.
Yeah.
How does Amazon Verified Permissions, AVP, compare? It's a managed service.
Right. AVP is an AWS managed service, which is a big difference operationally, and it's more specialized than OPA. It uses a different policy language called CEDAR, which Amazon designed specifically for application level authorization, defining permissions on your application's resources, like documents, folders, etc.
So not for controlling AWS resources themselves, that's still IM.
Exactly. AVP is for your application's authorization logic, not AWS infrastructure. CEDAR is built around principles like least privilege and analyzing policies for safety. Being a managed service also means it integrates nicely with other AWS services like CloudTrail for logging and monitoring, which is a plus.
CEDAR, REGO, different languages, different focus. Choice depends on your ecosystem and needs, I guess.
Pretty much. OPA offers flexibility and vendor neutrality. AVP offers specialization for application authorization within the AWS ecosystem and managed operations.
Now, a critical challenge for any SaaS platform using these. Multi-tenant isolation. How do OPA or AVP ensure tenant A can't possibly access tenant B's data?
This is crucial. You absolutely cannot have policy mistakes allowing cross-tenant access. There are two main approaches to structuring your policy store. The ideal, often considered best practice, is the per-tenant policy store.
Meaning each tenant gets their own separate set of rules.
Exactly, like a silo model. Tenant A has policy storia, tenant B has policy store. When a request comes from tenant A, the PP knows to query only tenant A's store. If tenant B has some custom rule, it only exists in their store.
That sounds safest. Maximum isolation. Errors in one tenant's policies can't affect others.
Precisely. It simplifies auditing for specific tenants, too. The downside is potentially more operational overhead managing all those separate stores.
That's the alternative.
The one shared multi-tenant policy store. Here, everyone's policies live in the same place. It's often simpler to manage from an infrastructure standpoint.
But sounds riskier. How do you guarantee isolation?
You have to be extremely careful with your policy writing. The non-negotiable first step is a foundational deny or forbid policy that blocks all cross-tenant access by default.
How does that work?
It checks an attribute, let's say, tenanted on both the user making the request, the principal, and the resource they're trying to access. The default policy says, deny unless principal.tenanted equals resource.tenanted. Only then do you evaluate other, more specific, allow rules.
So access is only even considered if the tenant IDs match. It relies heavily on that one rule being perfect.
Absolutely. It requires rigorous testing and careful policy design, but it can work. It centralizes management but shifts the burden to meticulous policy crafting.
Okay, managing these policies is key, but like you said, even the best policy engine is useless if the underlying infrastructure isn't secure. These PDPs, they run somewhere.
Yep. They run on servers, in containers, on Kubernetes, in the cloud. If your cloud configuration is weak, say, the S3 bucket with tenant data is accidentally public, or the IAM role running the policy engine has way too many permissions.
Then the fancy authorization logic doesn't matter much.
Exactly. The whole stack needs to be secure.
Which is why understanding your cloud security posture is so vital. You need to know if things are configured correctly, if you have excessive permissions, if data stores are exposed.
Continuous assessment is key.
And that brings us to our sponsor again. If you need that kind of continuous, unbiased view of your cloud environment to ensure everything supporting these secure systems is locked down, check out Cloud Assessment from VibeHack. It helps find those misconfigurations. Find it at cloudasses.vibehack.dev. All right, let's shift gears. We've focused a lot on the back end, the brain. Now let's talk about the client, the mobile app itself, running out there on devices you don't control.
The public client, yes.
And this brings us to what you call the client credential trap. You sounded quite passionate about this one needing to die.
Maybe a little. But it's a fundamental misunderstanding that causes so many problems. It comes from treating a mobile app or a browser-based single-page app, SPA, like it's a confidential client, like a secure back-end server.
They can't keep secrets.
Exactly. The client credentials grant type in OMOLATH was designed for server-to-server communication, where one server can securely store a client secret. Mobile apps run in untrusted environments. They cannot securely store a secret.
So embedding that cliented and client secret pair directly in the mobile app's code or config files, bad idea.
Terrible idea, because it's trivial for an attacker to get them out. Download the app package, APK for Android, IPA for iOS, decompile it. The secrets are often just sitting there in plain text in a config file like appsettings.json or hard-coded in the code.
Even if they try to hide or encrypt it.
A determined attacker can still find it. They can use runtime analysis tools, hook into the application's memory on a rooted or jailbroken device, and just observe the secret when the app actually uses it to make an API call.
And once the attacker has the app's cliented and secret,
they can impersonate the application itself. They can make API calls directly, potentially bypassing user authentication entirely, depending on how the API is set up. It's a huge security hole.
Okay, so client credentials grant for public clients equal NO. That's the right way, the modern gold standard.
The standard, the required way now, is the authorization code flow with proof key for code exchange. PKCE, pronounced Pixie.
PKCE.
Okay.
How does PKCE work without a secret? How does it secure the flow?
It cleverly replaces the static, long-lived client secret with a dynamic, one-time use secret generated on the client. Here's the flow.
Lay it out for us.
Okay. First, the mobile app, before starting the authorization process, generates a random high-entropy string called the code verifier. Think of this as a temporary single-use secret. It keeps this verifier private.
Stays on the device. Got it.
Then the app takes that code verifier and transforms it using a standard hashing function, usually SHA-256, sometimes with base 64 encoding. The result of this transformation is called the code challenge.
So challenge is derived from the SQL verifier.
Exactly. Now, when the app redirects the user to the authorization server to log in, it includes this code challenge and the hashing method used in the request. The authorization server stores this challenge, associating it with this specific login attempt.
Okay, server knows the challenge. User logs in, server sends back the temporary authorization code.
Right. Now, the app needs to exchange that authorization code for the actual access token. When it makes that request to the token endpoint, it includes the authorization code and the original secret code verifier it generated back at the start.
It reveals the secret verifier only at the very last step.
Precisely. The authorization server receives the code and the verifier. It then performs the same transformation, the SHA-256 hash, on the submitted code verifier. It compares the result to the code challenge it stored earlier.
And if they match?
If they match, the server knows this token request is coming from the exact same client instance that started the process. It issues the access token. If they don't match,
It means someone intercepted the authorization code, but didn't have the original secret verifier. Request denied.
exactly. It binds the authorization code to the specific client session that initiated it, defeating interception attacks. Like if malware on the phone tried to steal the code via a malicious redirect, PKCE is non-negotiable for public clients.
Crystal clear. Okay, so we've securely obtained our tokens, the short-lived access token and the longer-lived refresh token. Now we need good token management and session hygiene on the device itself. Where do we store these things?
Absolutely critical point. You must use the secure, encrypted storage provided by the operating system. On Android, that's encrypted shared preferences. On iOS, it's the keychain.
Why those specifically?
Because they leverage hardware-backed encryption where possible and provide process isolation. The stored tokens are protected from other apps snooping around. What you absolutely never do is store tokens in insecure places like the browser's local storage if it's a web context within an app, or standard shared preferences on Android, or just plain files.
Because those are vulnerable to what? XSS file system access on rooted devices.
Both. XSS can steal from local storage. Root access makes standard file storage trivial to read. Use the OS-provided secure elements.
Okay, secure storage, lockdown. What about token lifetime? We want to minimize the damage if a token does get compromised, right?
Yes. Short lifespans are key. Access tokens, like JWTs, should expire quickly. Maybe 15 minutes, maybe even 5 minutes, depending on your risk profile. You also need strict session timeouts based on user inactivity.
And the refresh token handles getting new access tokens without forcing the user to log in constantly.
Right. Refresh tokens have longer lifetimes, hours, days, maybe weeks. But even they need careful handling. And this brings us to an important technique: token rotation.
Rotation, how's that different from just using the refresh token until it expires?
With basic refresh, you use the same refresh token over and over. With rotation, every time the client successfully uses the refresh token to get a new access token, the authorization server issues a brand new refresh token alongside the new access token and immediately invalidates the refresh token that was just used.
So each refresh token is essentially single use.
Pretty much. This provides a powerful defense against refresh token theft. If an attacker steals a refresh token and tries to use it after the legitimate user has already used it and thus rotated it, the server will detect that the stolen token has already been consumed and invalidated.
It acts like a replay detection mechanism.
Exactly. It can immediately flag the compromised account and potentially invalidate the whole session. It's more complex to implement, especially coordinating invalidation across distributed systems, but it significantly boosts security.
Makes sense. We also touched on adaptive authentication, tying security posture to risk.
Yeah, this is about dynamic risk assessment during the session.
Yeah.
Is the user suddenly coming from a different country, a brand new device? Are their interactions looking suspiciously automated?
Huh?
Based on these risk signals, the system can adapt. It might require the user to re-authenticate, maybe step up to multi-factor authentication, MFA, even if they passed it initially, or it might just shorten the session lifetime. It's about reacting to changes in perceived risk.
And you mentioned privilege changes too.
Critically important. If a user's permissions change mid-session, maybe they're granted temporary admin rights. You must invalidate their existing tokens immediately and force them to get new ones that reflect the new, correct permission set. Don't let old tokens linger with outdated privileges.
Okay, good hygiene. Now, network level. Network resilience and encryption. HTTPS TLS is baseline, obviously.
Mandatory. Non-negotiable for anything transmitting sensitive data. TLS uses asymmetric crypto for the initial handshake verifying the server and agreeing on keys, then switches to faster symmetric crypto for the actual data flow.
But sometimes we need more, like for messages or financial data.
Yeah, for highly sensitive payloads within the TLS tunnel, you should consider end-to-end encryption, E2EE. Using strong, well-vetted crypto libraries, think Signal Protocol as the gold standard to encrypt the data before it even hits the TLS layer. This means only the true sender and final recipient can decrypt it, offering protection even if the intermediary servers are compromised.
Okay. Now, the advanced technique for mobile specifically, certificate pinning, this is about stopping man-in-the-middle attacks, right?
Exactly. It's a powerful defense against sophisticated MITM scenarios, like compromised certificate authorities or rogue Wi-Fi networks trying to intercept TLS traffic using fake but trusted certificates.
How does it work? You hard code something in the app.
You essentially embed the expected public key, or a hash of it, or the entire certificate of your back-end server directly into the mobile app's code during the build process.
So when the app connects,
It doesn't just rely on the device's standard trust store of CAs. It explicitly checks, does the public key of the certificate presented by the server match the exact key I have pinned? If there's any mismatch, even if the certificate chains up to a trusted CA.
the app refuses the connection, instantly blocks the MITM attempt.
Correct. It creates a very rigid trust anchor. But, and this is vital.
The operational caveat.
Yes, you must implement pinning with a backup pin. Pin the public key of your current server certificate, but also pin the public key of a spare certificate you hold in reserve, or maybe the key of an intermediate CA you control.
Why the backup?
Because if you only pin the primary key and that certificate expires or gets compromised and you need to revoke and replace it quickly, your app will suddenly stop working for all users. It can't connect to the new valid certificate because its key doesn't match the old pinned key. The app is effectively bricked until you force everyone to update.
Ouch. So the backup pin provides a fallback path for rotation without breaking the app.
Exactly. It's crucial for operational sanity with pinning.
Got it. Lastly, for the client, self-defense. RASP and obfuscation, protecting the app when it's out there in the wild.
Right. RASP stands for Runtime Application Self-Protection. Think of it as embedding a security agent inside the application itself.
What does it do?
It actively monitors the environment the app is running in. Is someone trying to attach a debugger? Is it running on a rooted jailbroken device? Is it inside an emulator known for malware analysis? Has the app's own code been tampered with since it was installed?
And if it detects something suspicious,
It can take immediate defensive action based on pre-configured policies. It might shut itself down cleanly, it might selectively wipe sensitive data stored locally, or it might just send an alert back to your servers. It's about making dynamic analysis and tampering much harder.
and you said RASP works best with code obfuscation.
Yes, they're synergistic. Obfuscation happens at build time. It scrambles the application's code, renames classes and methods to meaningless strings, removes debug symbols, maybe adds confusing control flows.
Doesn't stop a dedicated attacker, but makes their life harder.
Much harder. It significantly increases the time and effort needed for reverse engineering, just figuring out what the code does or where the interesting dits are. So obfuscation acts as a passive deterrent, slowing the attacker down. RASP is the active defense that detects them when they finally try to hook into or modify that obfuscated code at runtime. They work together to protect the app's integrity. Okay, we've hit architecture, policy, client security. Now we need to weave this all into how we actually build software, operationalizing it. This is DevSecOps territory.
And the core principle there is shift left, right? Moving security earlier in the process.
Exactly. Don't wait until the final QA phase or worse, production to find security flaws. Embed security thinking, security tools, and security checks right from the design and coding phases. Make it part of the developer's daily workflow.
It becomes everyone's responsibility, not just a separate security team's problem at the end.
Precisely. Empower developers with the right tools and training. Integrate automated security scanning into their IDs, into the CI/CD pipeline for every commit, every pull request. Finding and fixing flaws earlier is exponentially cheaper and faster.
And that integrated testing shouldn't be just one thing. You advocate for a comprehensive testing trio: SAST, DAST, and manual pen testing. Let's break those down. SAST first.
SAST, static application security testing. Think of it as automated code review for security bugs. Tools like SNCC, SonarQube, checkmarks. They scan the source code, the bytecode, the dependencies without running the application.
What kind of things does SAST find?
It's good at finding known bad patterns. Things like hard-coded passwords or API keys, use of known insecure functions, potential SQL injection points based on code structure, outdated libraries with known vulnerabilities, that's software composition analysis, often bundled with SAST. It checks the code structure.
Okay, static analysis, then DAST.
DAST, Dynamic Application Security Testing. This tests the application while it's running. Tools like OWASP, Zapier, or Burp Suite Pro act like an attacker from the outside. They send crafted, often malicious requests to the application's interfaces, APIs, web pages, and analyze the responses.
What does DAST catch that SAST might miss?
Runtime issues, things related to configuration, how different components interact, session management flaws, issues with HTTP headers, authentication authorization problems that only manifest when the system is live. It tests the application's behavior in a running state.
And the third leg of the stool: manual penetration testing. Why do we still need humans if we have these automated tools?
Because the tools are great at finding known patterns and common vulnerabilities, but they're generally terrible at understanding business logic or finding complex, multi-step attack chains that exploit subtle design flaws. Remember that context-based escalation example?
Yeah, the e-commerce cart manipulation.
A human tester, an ethical hacker, thinks creatively like an attacker. They'll try to understand the application's purpose and workflows and find ways to abuse them that automated scanners just wouldn't conceive of. They provide that crucial outside-in adversarial perspective. You need all three, SAST, DAST, and manual testing for comprehensive coverage.
Makes sense. Okay, another huge operational challenge, especially with CI/CD, managing secrets, API keys, database password certificates.
Oh yeah, this is a constant source of breaches. The cardinal sin is hard-coding secrets directly in source code, config files, environment variables checked into Git, or build scripts. Just don't.
So what's the right way? Use a vault.
Yes. A dedicated secrets management system is essential. Things like HashiCorp Vault, Azure Key Vault, AWS Secrets Manager. These are hardened systems designed specifically to store secrets securely with encryption, access control, and audit trails.
And the application retrieves the secret when it needs it.
Exactly. At runtime, the application authenticates to the vault using a secure identity mechanism like an IAM role or Kubernetes service account and pulls the secret it needs, often just into memory. The secret itself never lives on disk in the codebase or config files.
And these vaults also help with proactive key rotation.
They make it feasible. Rotation should be automated and policy-driven. Configure the vault to automatically rotate keys, database passwords, API keys on a regular schedule, maybe every 90 days, maybe every 30 days, maybe even daily for highly sensitive keys.
Reduces the window of opportunity if a key is compromised.
Massively. If a key is only valid for 24 hours, the potential damage from its compromise is limited. Rotation should also be triggered automatically by your CI/CD pipeline whenever infrastructure changes, or manually immediately if a user's role changes or they leave the organization. Old tokens and keys associated with changed privileges need to be invalidated now.
Good discipline. Okay, let's circle back to the API gateway. We mentioned it as part of the PDP architecture, but it plays a broader defensive role too, right? It's the front door.
Absolutely. Your API gateway, like a AWS API Gateway, Azure API Management, Kong, Apigee, is a critical enforcement point. It handles several security tasks before traffic even reaches your backend services.
Like what?
Foundational stuff. Rate limiting and throttling are huge. Protecting your backend from denial of service attacks or simple resource exhaustion caused by buggy clients or brute force attempts.
Okay, traffic shaping. What else?
Often it handles the initial authentication check, validating JWTs, API keys offloading that work from every single microservice. It can terminate TLS SSL, ensuring encryption from the client. And critically, it's a prime location for input validation.
Checking the incoming requests for bad data.
Yes. Remember the mantra, never trust data from the client, never. The gateway can enforce schema validation on request bodies, check for expected headers, validate parameter formats and ranges, and reject malformed or suspicious input before it gets anywhere near your application logic or database.
And for SQL injection specifically, you mentioned the ultimate defense earlier.
Yes. While input validation at the gateway helps, the definitive defense against SQL happens at the application layer, where the database query is actually constructed.
Right.
Use parameterized queries.
Right. Also called prepared statements. Remind us why they're so effective.
Because they fundamentally separate the SQL command logic from the data being inserted or queried. You first send the structure of the query to the database with placeholders for the variables. Then you send the actual user input separately.
So the database knows the input is just data, not part of the command.
Exactly. It treats the user input string, even if it contains SQL commands like drop table, as literal data to be inserted or searched for. It never gets interpreted or executed as a command. It breaks the mechanism SQL relies on. Use them, always. Full stop.
Got it. Parameterized queries are non-negotiable.
Pretty much.
Go. This whole shift towards automation, CI/CD integration, embedding security testing, it really defines modern high-velocity development, doesn't it?
It has to. You can't bolt security on at the end anymore if you want to move fast. It needs to be built-in, automated, part of the culture.
And achieving that level of integration, making sure your pipelines support SaaS, DAS, secrets management, policy checks without slowing developers down. That's the goal.
It's the core of practical DevSecOps.
Which leads us to our sponsor once more. If you're looking to operationalize this, embedding security smoothly into your development workflows, VibeHack's DevSecOps solutions focus on automating these security practices within CI/CD. You can learn more at devsecops.vibehack.dev.
One last operational piece. Monitoring and observability. Don't forget logging.
Right. Log everything.
Well, logs strategically but comprehensively. Every API access attempt, successful or failed, especially authentication and authorization decisions, any significant errors. It all needs to go to a centralized logging system, CloudWatch, Splunk, NeoKStack, whatever.
Why centralized?
For incident response and auditing. When something goes wrong, you need one place to quickly search and correlate events across all your services to understand what happened. Scattered logs are useless in a crisis.
And when things do go wrong, how should the API respond to the client? Error messages.
Keep them generic. Never, ever return detailed internal error information like stack traces, database error codes, or internal file paths back to the client.
Because attackers can use that information.
Absolutely. It gives them clues about your system architecture, technologies used, potential vulnerabilities. Just return a standard generic error message like an internal server error occurred and log the detailed error internally for your own team to debug. Don't leak internal detail. Hashtag outro.
Wow. Okay, we have covered a lot of ground today, from high-level policy down to very specific crypto details for mobile apps.
It's a deep topic.
It really is. But the core message seems clear. Security has to be layered. There's no single silver bullet.
Exactly. Think of that castle analogy. You need the strong outer wall of the API gateway with rate limiting and input validation. You need the internal controls, the decoupled policy engine, like OPA or AVP, handling fine-grained authorization with proper multi-tenant isolation.
And for the client side, the mobile app itself. Ditch client credentials. Use PKCE for the auth flow. Store tokens securely in the keychain or encrypted shared preferences. Use token rotation. Consider RASP and obfuscation.
And operationally, shift left. Use the testing trio SASDATH down tests, manual pen tests. Manage secrets properly with a vault and automated rotation. And please use parameterized queries against your database.
That's a solid checklist. Okay, time for our final provocative thought. We spend this whole time talking about users Alice, Bob, the admin, as the principal being authenticated and authorized.
Good human element.
Right. But you briefly mentioned things like the model context protocol, AI agents acting on behalf of users, using their own restricted tokens via oath.
Yes, the rise of machine principles. Autonomous agents performing actions.
So here's the question. How does authorization policy need to change fundamentally when the principal, the actor, isn't a human with human behavioral patterns, but an autonomous piece of code, a machine identity?
Ooh, that's a big one. Because so many of our advanced techniques, especially in ABAC and adaptive authentication, rely on observing behavioral anomalies. Humans have patterns, machines acting at scale. Their normal behavior is different. Their attack behavior might also look different.
So how do you write policies for them? How do you detect a rogue AI agent versus a legitimate one if they both just make API calls incredibly fast?
Exactly. Our current anomaly detection might fail. We probably need to shift towards policies based more on the declared intent or the scope granted to the agent via its token, and rigorously verifying that scope against the requested action and resource. Can we cryptographically bind an agent's identity to its approved operational parameters? How do we handle credential rotation for potentially millions of autonomous agents? What new attack vectors emerge when the user can operate at machine speed and potentially learn and adapt its attack strategy?
Defining and enforcing policies for machine intent, not just human roles or attributes.
Yeah,
That's a whole new frontier for authorization.
it really is. Something for everyone to start thinking about as these agents become more common.
Definitely food for thought. Well, thank you for guiding us through this incredibly complex landscape today.
My pleasure. It was a great discussion.
And thanks to all of you for joining us on the deep dive. A final thank you to our sponsors, vibehack.dev, cloudassist.vibehack.dev, and deadsecops.vibehack.dev. We'll see you next time.